The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we should celebrate the Nobel Prize is for imaging this time. Of course fiber optics, but who cares about fiber optics? But it's also about light and imaging. And this is the point I was making just a couple of weeks ago about how, in imaging, you keep on getting Nobel Prizes, but somehow in other fields, just no Nobel Prizes. Of course, Ted Adelson sent out an email. I don't know if he told you this. And he thinks prizes like Nobel Prize and all that have, outlived their importance, because they were always trying to feed this notion that science moves by select group of people working in select places and coming up with amazing discoveries, like select individuals. And we know that's not how the world works now. Even the development of fiber optics is not just one person or one team, but hundreds of people have made tremendous contributions. And the same with CCD chip, for which there was a Nobel Prize. And somebody may have thought about it, somebody may have implemented it, but at the same time, there are a lot of people involved. So it's somewhat misleading to identify one or two people as the ones who made all the difference. By the way, the inventor of Lightfields, which we're going to talk about, Lippmann, also got a Nobel Prize. But he didn't get the Nobel Prize for Lightfields. He got a Nobel Prize for inventing color photography, which is very closely related to Lightfields. It's surprising. We'll discuss about that today. Let's figure out. So the assignment actually has two options, of course. And the Lightfield part has several parts, several subparts. But don't get intimidated by all the things you have to do. It's mostly a matter of, how much you want to do. And based on your background, so if I know you have a lot of background in light fields and so on, so like Rohit over there, for example, I would expect him to go quite a bit deep in the assignment. But those of you who don't have as much optics background, or those of you who are using, are not programming and using, or don't have programming background and using some GUI-based tools to do the Lightfield assignment, of course I'll expect you not to just finish the first part, but not first subpart, but not all the parts. So we will kind of normalize your performance based on your background and abilities. So you may want to send an email to me separately in case you run into problems and say, hey, I don't have as much background in this area. But the assignment is basically taking pictures and taking an average of those pictures. So it's just that when you have to take a picture, shift it, and add to some other picture. So the concepts are really simple. And if you do the first subpart, you should be able to do other subparts very quickly if you think about it some more. But again, given that you have limited time, you don't have to go all the way. All right. So what I'm going to do is actually start talking about the light fields, and then halfway through, we'll come back and talk about the assignment. Okay. So if you're in photography or you're new to cameras, people always throw these terms at you: the f-stop, and fast lens and slow lens, and the bokeh and depth of field. And Ankit covered it a little bit, but it's always very confusing. And photographers, just like any other cult group, always try to make it more exotic and more difficult to understand what they're saying. So my general advice is, as a researcher, as a student, as a scientist, just get rid of all the jargon and focus on really simple parameters. Okay. So f-stop, for example, is really complicated. And it's not just it's complicated, but it's actually wrong. the numbers they use are actually wrong. They are off by sometimes up to 10%. Increasing the f number or decreasing the f number is not very clear what it means, because it's inverse of an f2.8 versus f5.6. The 5.6 actually is smaller than 2.8. Whoever came up with that? In microscopy and scientific imaging, they use numerical aperture, which is more meaningful, because when aperture becomes larger, the numerical aperture becomes larger, and it's thought about it in a scientific way. So let's see. So the whole concept of light field might seem very foreign, and you'll wonder why we need to study it. But once we have understood this relationship between 3D points to 2D pixels and rays and relationship between different rays and so on, all these other concepts such as depth of field and f number and all that will become extremely clear. And you won't think of them as some abstract quantities, but quantities with some real meaning to it. All right, so this is how we started thinking about the ray space. And then we realized that rays are 5-dimensional because there's a point and direction. So 3 degrees of freedom for the point, and only 2 degrees of freedom for the direction. Why is it not 6 degrees of freedom as we have elsewhere? Usually have 3 for translation, 3 for rotation. Here we have 3 for translation, only 2 for rotation.
Because there's no elevation.
Sorry?
There's no elevation
that's a different parameter. There is no rho, right? We ignore that. But then we realized that sometimes you don't have to use 5 dimensions. You can get away with 4 dimensions. In which case does that happen?
The dual plane approximation.
2-plane approximation, but that's good. But why does it allow you to go from? Why can't we go from 5D to 2D? Melissa? Did you raise your hand? Okay. Let's take the next one.
You're only caring about a single ray or a single point?
Exactly. So if you don't have this occluder in the middle, the intensity on this side is going to be the intensity on the other side. So you can just use it as a 4-dimensional quantity. And now the 4-dimensional quantities we can specify in multiple ways. We can either specify it as a 2D position and 2D angle, or we can do it as a 2-plane parameterization where you have 2D point on one plane and 2D point on the other plane. And this is kind of in the 3D world. So UV coordinate on this plane and ST coordinate on that plane, and that defines the ray direction. Now, what's the disadvantage? I'll just go back to this. So you'll realize that when we are talking about all this optics and rays and geometric quantities, we'll always think about them in flatland. Okay, so real world is 3D and rays are in 4D space, but for the sake of discussion, our world is just 2D, the flatland, and the rays are how many dimensions? 2 dimensions. Okay, so something strange is going on already, right? Because we went in a 3D world, the rays are 4D, but in a 2D world, the rays are 2D. Right? There's already a mismatch going on, and as we go forward, you'll realize where that comes from. Okay, so most of our discussion will stay in flatland. So our world is 2D, our rays are 2D. There is 1 degree of freedom for the position. In this case, 1 degree of freedom for the position and 1 degree of freedom for the angle. Okay, so that's the 2 dimensions for the ray. We can either express it as position and angle or as position and position. Okay. Now, that seems pretty good. There are some rays here which cannot be represented very well with this representation. Which it's okay to represent them here, but they cannot be represented here. Which ray is it here? Yes?
Ones that are parallel to the plane?
Exactly. So if a ray is vertical here, it will never intersect both planes. So it's difficult to express that. in this particular formulation. And if you're thinking about the implementation, then any ray that's, even if it's not vertical but close to vertical, will have sampling issues. You won't be able to represent that very well. And here you don't have that problem because you're going to you'll use a different 3D position, and theta phi is always defined. So that makes it very simple. All right. So now, if you can build this a matrix, the machine that can see everything everywhere in every wavelength, how many dimensions is that? 7 dimensions, right? 5. So we go back to this one. 5 dimensions here plus wavelength and time. Okay. Now we're going to get closer and closer to that matrix that sees everywhere. And we're going to start with a camera array. And we're going to say that an array of cameras can capture light field. Okay? How does that happen? Here we have, imagine on this plane, I'm going to put a set of cameras. And for every camera, its frame buffer, I'm going to indicate as S and T. Okay? So every camera position here is given by UV coordinate, and the frame buffer of each camera is specified by ST. Pixel is ST. Okay? So this is how we have the UV plane. I'm going to put a camera here, right? And then I have the ST plane. And what I'm going to say is, for this camera, I'm going to shoot all these rays. Okay. So as you can see, the image starts becoming very messy in the real world. So we'll go back to Flatline. Maybe I can draw it here for now. So this is my U plane, and this is my S plane. Okay. And I'm going to put a camera here, camera here, camera here, and camera here. And when I say place a camera there, I really mean the center of projection, the pinhole of the camera is placed here. Okay. So I put a pinhole camera here and the sensor back here. Right? And what that is doing is, if I take every pixel through this pinhole, then it's shooting the ray out here. Again, we're going to think like the Greeks. So the camera is shooting rays out in the world. The world. And the coordinate of these pixels now is given by S, but the position of each camera is given by U. So maybe this is U equals 1, U equals 2, U equals 3, U equals 4, and so on. And similarly on S coordinate, whatever it goes from 1 to 1000, let's say, this is coordinate. And we're going to say that this camera can capture all the rays that pass through. And then this camera again is going to pass all the rays that come through it. Okay. So very similar to your assignment. I'm going to take a camera, shift, and it's going to capture all those rays. Certain rays are missing here that we're not able to capture. Which rays are those? So we're capturing. If I take a photo from here, I basically captured 1,000 rays, right, corresponding to each S coordinate. If I go here, I captured another 1,000 rays. So in this picture, I have captured about 4,000 rays. And I'm using the rays in without specifying what it means, but I think you have a notion of rays, some kind of a pipe, which you're looking at. So what's missing?
The points between two cameras.
Exactly. So anything that went at U equals 0.5, those rays are not being captured. Right? So that's how life is. The world is continuous, and somehow we have to discretize and sample. Okay. But that's fine. It's close enough for us to start representing the world in a 4D representation. So now, if somebody asks you, what's the dimensionality of the world? People of course say, yes, it's 3D. But what does this tell you? The appearance of the world is actually 4D. And it's always a difficult concept to get across. But some other ways of thinking about the same situation is imagine if you build a hologram. Okay. You have a hologram and you're standing in front of it, and the hologram has a coordinate system as t. And as you move your head, you see a new image coming out of this hologram. Right? So if I move in the u direction, I see a different set of images. So, but if I move my head up and down, then again I need to see new images. Right? In the v direction. So the hologram also is recording four-dimensional data set, or a lenticular display, not lenticular but lens-based display, is also recording a 4D information. So to record a view through a window, for example, I need to actually store a four-dimensional data set in a two-dimensional film. And that's the display problem. And this one is actually the inverse of that. We're going to capture the world. And when you capture the world through the window, again we need to record a four-dimensional model. So try having that argument with your friends, whether the world is a 3D or 4D. So maybe in the 21st century, we have gone one more dimension. All right. So now we have array of cameras, and we're going to think about how that can be achieved, not with an array of cameras, but just with a single camera. So the array of cameras is very much similar to this, just a set of cameras with a bunch of sensors behind it. And as far as photography is concerned, we want to think about how we can achieve that with just a single camera. So there are a few concepts we are going to look at more carefully. One is that an image that's created for a 3D point is actually a sum of multiple images created by different parts of the lens. Okay? So if you have a whole lens and you cover all these parts and leave this one open, it will create one image. Then if I block that one but just leave this one open, you'll get another image, and so on. And in this case, I will get, I guess, 5 different images. Now, what's the difference between those 5 images? You can already kind of see the hint here. Right? It's as if I've placed a camera here, then I placed a camera here, then placed a camera here, and here, and here. Right? So it's just like opening up part of the aperture or sub-aperture. It's just like moving a camera, but within the aperture of your lens. If your aperture is only about 25 millimeters, the whole shift is only about 25 millimeters. But there's a difference between this situation and this situation. Okay? So, because all these are pinholes and there's no optics in it, and this one has pinholes, but there's some special shape. If you just look at any one section, what does it look like? Don't look at the whole lens, just look at any one section. Sorry?
A trapezoid.
Trapezoid, which is a truncation of a prism. Right? So you can think of a lens as being made up of sections of a prism. And of course, this prism is truncated here. And this prism is truncated here. And this one is just a slab of glass. It's parallel. So it's just a flat piece of glass. It doesn't really do anything. And so in high school, when they say, when the light goes to the center of the lens, it doesn't change light. It's just slab of glass. Of course, light goes straight. And here we have prisms, so light goes in and it deflects. So we just have a set of prisms. Here we just have a set of pinholes. So let's assign some of those coordinates one more time. Okay? We're going to say the camera position, right? The camera position here is given by u. and the pixel position is given by S. Okay, you can ignore the second variable here. And we're going to try and understand this four-dimensional space that the camera is capturing. Okay? I'll give you the punchline here, which is if a camera can capture this four-dimensional representation of light, it has captured everything that's coming through that lens. Okay? And it includes phase and all that information. So all the geometric information about the world is completely captured by this four-dimensional representation. So once you have that, of course, you can go back and do anything you want. You can do digital refocusing, you can estimate 3D shape, you can insert new objects in it, whatever you want. That's all you can get. So just by going 2 dimensions higher, from 2D to 4D, it's a complete representation. And that's why it's so important to capture that 4D light field. Because if you want to think about any sophisticated photography applications, that's the maximum information you can get. We still have wavelength and time and polarization and so on, but those are not geometric dimensions. The geometric dimensions are just space and angle or true space and so on. All right. So, as I said, we're going to think of the lens as being made up of a sequence of prisms. Okay, and when you capture a light field, you end up getting an image that looks like this. So the picture from here versus here versus here versus here will have a small parallax as you move around. It will look almost the same, but there'll be a very tiny parallax. So if you look at this set of images, they look almost the same, and they're captured by a light field camera. But if you see very carefully, then the distance between the eye and the ear of the bunny is changing from top to bottom. Okay, here it's almost touching the eye, and over here there is a significant gap between the two things. So there will be these small gaps, and I'm sure when you do this experiment where you look at something with left eye versus right eye, it seems to shift. Your finger seems to shift. And that's the parallax that you're introducing. And that's the same effect that's happening here, because the parallax between your eyes is only about 6 centimeters, but that's sufficient to create a shift in relative pixel positions.
What's the method for capturing phase?
So we'll come and discuss that. So it's a very important question. All right. And Mark Lavoie and his group at Stanford are world leaders in thinking about many types of light field cameras and also their applications in different areas. So I've taken a lot of slides from his presentations, and he has also applied it for microscopy and so on. All right. So very briefly, make sure I'm on the right. Okay. Very briefly, there are other ways you can represent rays. So right now we're thinking about a UV plane and an ST plane and just an intersection of that. But depending on your application, you may have some other ones. Maybe you have a sphere, and you can cut the hemisphere, the two hemisphere, and any point on this hemisphere and any point on that hemisphere together will create a ray as well. In some certain cases, you want to create some convenient 2D manifold, and the position of that manifold and the theta phi with respect to that can also be a light field. So just those of you who think about it mathematically, there is a continuum between flexible light fields to two-plane parameterization of all right. So let's come back to talking about light field inside the camera. Okay. So why doesn't a traditional camera capture this 4D light field? Okay. So if I have a point in sharp focus, the rays from that emanate, they bend at the lens, and they converge to a photodetector. And all the radiance along different directions is integrated together to get and that's recorded as the intensity of that pixel. So what you get out there is just 2D. So flash sensor, you get a 2D image. The question is, what do we get extra when we capture a 4D light field? in terms of this diagram?
So right now it's compressing all the angles into single pixels, but you can extract the angles.
Exactly. So this is the most important question. Remember, I'm repeating it multiple times, but now we want to figure out not just the total of all these rays, but also the value of each of these rays. Okay. And where do the rays come from individually? They're coming from different parts of the lens. So there's a very interesting relationship between the lens and the sensor. And if you realize that geometric relationship, we may be able to recover this 4D light field. So Ted Edelson and his student came up with an idea in 1992 to try and build a compact device. The original idea was again presented by Lippmann in 1908, more than 100 years ago now. So the concept of light field has been around about 100 years. And then Renning at Stanford in 2005 created this really beautiful device that can very compactly capture a light field as well. The basic idea is very straightforward. You move the sensor a little bit further back, just a few micrometers, and then replace this plane with a set of microlens array. And if you just look at these two here, it's very similar to the lenticular display or microlens-based display that you see on cereal boxes and rulers and so on, right? But now we're going to use that for imaging rather than for display. And this is how they built the device. They place these microlens arrays. The pitch of each microlens is 125 microns. And the pixel itself is about 9 microns. So under each microlens array here, you have about 9 by 9 pixels. Sorry, 14 by 14 pixels, I'm sorry. And then, so what they're going to do is they're going to record the incoming light in 14 different directions. Okay. That basically means that they're going to slice the lens into 14 segments, and they're going to capture the light that would have appeared if I just opened the first part of it and blocked the remaining 13. And then I unblocked only the second one and blocked everything else. So the 14 pictures that I would have taken by exposing only one sub-aperture at a time, you can capture that in one shot. Yes?
So I have a question about the lenslet array. Do any of the rays ever go outside of that 14 by 14 area and hit a different little thing? So
instead of coming from here, something from here might come and spoil the image.
Yeah.
That's a great question. That's a great question. And we'll come to that. And it basically relates to the F number, or the relative opening angles of the main lens and the micro lens.
But the goal is for that not to happen, right?
Exactly. Yeah. Not just it should not happen in terms of overlap, but you also don't want any black regions here. Mm-hmm. So you want to put the sub-aperture images as tight as possible. And we'll see some examples of that. Yes.
So why can't I just think of this system like without adding this microlens array?
Mm-hmm.
Why cannot maybe I can think of it as a system as like linear equations with unknowns, and if I know the parameters on these unknowns, then I can just solve. I don't really need to do an extra.
Excellent. That's a very good question. So those of you who think of this as some kind of a projection of a 4D space onto a 2D sensor, will say, okay, there must be some way I can recover the 4D image, 4D representation from this 2D image, right? And fact of the matter is, depending on the scene, you may be able to do it, but in general, this inversion is very unstable, right? Because, as I'll explain, because if you have, so what does it mean to actually capture this image? If I have something that's really sharp in focus, then all the rays have converged down there, right? So there's almost no information recorded about the variation between this and this and this, right? And let's say if I go out of focus, then I will get a blur here, and we'll look at that more, and all the blurs will go on top of each other. So it's basically, we are reducing the dimensions of the data set and hoping to kind of look up and recover the higher dimensional data set.
But even if something is in focus, So my understanding of what you are saying is that you probably cannot solve this in focus because you get linearly dependent equations.
Yes.
This is why. But I'm trying to understand why they are linearly dependent. Just because, I mean, if it's in focus and the summations, the coefficients of all the facts of all the variables are going to be very similar at every single sensor.
It's a bigger problem than that. Because remember, we're going from 4 dimensions to 2 dimensions. What you're saying is valid when we're going from 2 dimensions to 2 dimensions. Okay? But if I'm going from 4 dimensions to 2 dimensions, there is a significant, it's a lossy representation of the signal. If I have a very unique scene, which itself doesn't have a 4D light field going out, then I can recover it on 2D.
I'm thinking again like something along the lines of sensing, like the original thing did not really have full information.
Exactly.
But does that mean that I can actually solve?
In most of the cases, you
I
cannot.
want to get every 4 pixels or 4 pixels as original scene as like 1 pixel.
Yes.
Can I solve for that?
So, to rephrase your question, you're saying, how can I give up some resolution and recover a 4-dimensional representation, right? And that's exactly what's happening here with a help of some physics. So instead of thinking of this as just bare bones lens and sensor, if you take some help from physics and optics, then it turns out that that inversion is possible.
But why do I need it? I mean, is it like just numerical stability because the numbers are so small, or actually there really some physical process here that makes these equations linearly dependent?
It's just numerical stability. Yeah. I mean, first of all, you're going from 4D to 2D. Sometimes even going 2D to 2D, it may not be invertible. And here, because you're going from 4D to 2D, it's even more challenging.
Yeah, but we agree with the original 4D does not have complete 4D degrees of freedom
Exactly.
in the space. So
Exactly.
it should be possible to solve it.
So one good example of that is in astronomy, and we'll see it later, where you're looking at a star. And clearly, if you take a picture of a star, within the aperture of the lens, the star doesn't change that much. So clearly, it's a redundant data, and then light fields are used there to actually figure out the aberration in air. So that's an example we'll look at. But that's a very important question, because we'll always get into this. We always want to do more with less, right? So one motivation is I have a 2D sensor, but somehow I want to capture more information, right? And we're going to either use some optics and some physical techniques, or we're going to use some computational techniques. Right? So, and the best case scenario or the best strategy is actually to combine the two, combine a physical and computational approach to recover this more. Right? And the things we saw in the last class, for example, being able to tell whether an apple is real or fake, or being able to read a playing card and all that is a similar problem, right? Because the world is high dimensional and we only have a 2D sensor.
Okay, so one question about it. Wouldn't it be similar if I take the photo sensor and the top thing and just move it forward so that all the rays don't converge? I mean, I'm waiting to separate them. Why don't I get them before they converge?
You're thinking in the right direction. There are multiple ways you can recover all the 4D rays. You can, as I said, the simplest one would be to simply block part of it and take multiple pictures. So that's time multiplexing, right? This one is space multiplexing, because I'm giving up some resolution here to be able to recover the ray direction. So I'm trading off basically spatial resolution for angular resolution, right? And then the technique you're describing says, why not just move the sensor back and forth and take multiple pictures? And that's actually what's used in astronomy to recover the aberration in the sky and so on. So if you had just come up with that a few tens of years ago. Actually, 1967 is when phase diversity was, I believe, invented by a professor at Tufts. All right. So, just a teaser, I think we saw this earlier, that we can take this 16 megapixel image now, 4000 by 4000, but then because each microlens now will be treated as just one pixel, one metapixel rather. But under one metapixel, you have 14 by 14 pixels. So in terms of metapixels, you only have a 292 by 292 image. But because each metapixel has 14 by 14 underneath, we can do digital refocusing from a single shot. So this is spatial multiplexing, because we are trading space for angle. Okay? So here's an example where you said, okay, I want to give up 4 pixels to get angles for only 1 pixel. Right? So now we have given up 14 by 14 for 1 metapixel. But still, this involves using additional optics, and your dream is, can I do that without changing anything? Right? Is that correct?
Yeah. Can you put like the left part of the image in focus up close and the right part of the image in focus way in the back?
Yeah, you can do that, and that's part of the assignment. Having a slanted focus is now possible, as opposed to just planar change in focus. You can have focus that's not at a constant depth, but at some slant. And the tilt shift photography, which we saw in the very first class, where your angle between the lens. So typically, when you have a lens and a sensor, what's in focus is over here. And using the thin lens law, if I shift the sensor from here to here, then the plane of focus shifts from there to there. Right? So different things come into focus. But actually, if you tilt these guys, then the actual plane of focus goes somewhere here. And the Schlumberger principle says that this and this and this will all meet at one point. Okay? But with the Lightfield camera, you can do this directly. And you can decide this effect afterwards, after the photo is taken. The plane of focus doesn't have to shift as a slab, parallel slab, where it can be tilted and so on. So I highly recommend you to do that part of the assignment. You can skip the first one and just go for that. Because the way the refocusing is achieved, as we discussed last time, you're just going to take all these 14 images, in case of Flatline, and simply shift and add them. And how you shift and add them decides that plane of focus. If I don't shift and add, I focus at infinity. If I shift a little bit and add, I start focusing closer. If I shift more and add, I focus really close. But then I don't have to shift all of them the same way. Right? I can shift some of them more and the others less, and then I can focus on a tilted plane. Go ahead.
How feasible is it to assume that the pixel blur will be constant for a given depth of field, for a given depth?
What do you mean by that? Can you repeat?
So if I assume that for a given depth, which is out of focus,
right,
the pixel blur is going to be the same all over the scene. Is it a feasible assumption?
It's a reasonable assumption. It's a reasonable assumption that every point at a given depth will have the same amount of blur. When you start thinking about the lens aberration and so on, you will actually realize that this is true only in the middle part of the image, but as you go to the periphery of the image, you start getting some lens aberration effects. But to the first order approximation, you can assume that the whole plane has the same amount of blur. And that's what distinguishes a cheap camera from an expensive camera. Because for a cheap camera, the center is in good quality, but the periphery is not. And expensive camera will try to use multiple lenses and all kinds of tricks to make sure that particular statement is true. All right. So now we come to the part that kind of bridges the concept between scientific computing and Lightfields. So when you want to, there's this whole concept of adaptive optics, which is used in astronomy and telescopes and so on. And what basically it says is that if I'm looking at a star, which is very far away, then the wavefronts that are coming from the star should be mostly planar. Okay? So imagine I throw a stone in water, okay, and it starts creating the wavefronts. But if you go sufficiently far away, they become mostly planar with respect to each other. Okay. So if everything is clear between the star and where you are, all the wavefront should look clean. Okay? But if there is some disturbance because of hot air and so on, this will be distorted. So let's say this one there's hot air here, and there's nothing over here. Okay? Which is conceptually the same as putting a piece of glass here, and nothing over here. So here the light continues as it is, but over here, the light slows down and takes slightly longer to come out. Okay? And so the wavefront will look something like this. And as you go further, they all start looking like that. Okay. Now you can imagine there is another pocket of hot air somewhere here, and then this guy will slow down, so you'll start looking, something like that, and so on. Okay. So the wavefront is propagated. Now, the way it's thought about in scientific imaging is that if I want to take a picture of this star, which is far away, and the wavefronts are bent like this, the image that I will get will not be sharp, but actually will be blurred. Okay. And this happens to you, right? If you are just looking at in hot air or in a foggy scene, not foggy scene, but just if you look across the river to Boston, even on a clear day, because the temperature variations on the water versus land, the lights will not be sharp; they're a little bit blurred. And actually, over time, they seem to shift a little bit with a bit of a shimmer. And that's happening because at one instant it's bent this way, some other instant it's bent the other way, because the pocket is changing, the pocket of the air is changing up and down. So this is a big problem for telescopes, because they would like to see this very clearly, right? And this is an example where we know that we should be looking at something that's very far away and really doesn't have a 4D light. So it has a really simple representation. It's all black here, and there's some galaxy or some tiny thing over here. Very, very far away. So what I would like to do is take all these guys, and if I somehow can, by a different method, figure out what this disturbance is, I want to create a mechanism so that when it comes out, it's again back to nice and clean. So before that, I should say that in a normal situation, in a friendly situation, from a scene point, light goes out, it becomes parallel, and then remember this was a piece of glass which is thickest, right? So it slows down quite a bit, and here the glass is very thin, so it goes pretty fast. Right? So what comes in as a planar wave actually starts becoming a concave wave. So remember, this one slowed down the most, and this one slowed down the least. And this will converge down to a point. So this is kind of the wave propagation way of thinking about how the image is formed. And the ray representation would be, you have a lens, you have a point, rays are parallel, there's a prism, and each prism, the middle piece is just glass, it goes straight through. This one is a prism with only slight tilt, so the rays bend a little bit. This one is very steep prism, so light bends quite a bit, and eventually they form a sharp image. But they're equivalent. Okay? And by showing these two examples, what we realize is that we need to think about how different part of the lens impacts the incoming image. Right? So going back to this example where you want to deal with looking at something that's very far away, then I can, instead of imaging this distorted wave from here, I can first reflect it off some mirror. Okay? And what I'm going to do is the shape of this mirror is going to be exactly opposite of this particular guy. Okay? So I will do, I don't know, something like that. Okay? And when that goes through, even though it was bent this way here, when it goes out, it will be all parallel. And then I can put a lens and capture the image. So that's how it's done in astronomy. And this deformable mirror is deforming at thousands of hertz. And how do they calculate what the perturbation are? Anybody knows? They actually shoot a laser which ionizes at a particular height. So they basically create a virtual star. Sometimes they call it pilot star. And they take a picture of that, and they know that star is supposed to look like a point. So any change in the appearance of that star is an indication of how the air between the telescope and the stratosphere is impacting the incoming light. And so you can use that mechanism to correct for. So that pilot star basically acts as a calibration, and they will feed that signal to the deformable mirror, and it will correct that incoming wave. So if we have the same thing, you can go out in hot air where you have those mirages, on a street, on a highway, and or over water, and you can correct for it in real time. But this is really, really expensive.
Window, Mirage window, if you look through it, you see just like the effect of hot air.
So you want to correct for it, or you want to create an illusion that it's hot air outside? Yeah, I think you can. Yeah, that's pretty easy. It'll be a very interesting effect. In fact, what you can do is you can take a piece of glass, and the one key property of Mirage is that it's not just that you have an inversion. Everybody familiar with Mirage here? Where you have, it's Bob, right?
I'm
Sean, sorry.
Yes,
you got most of the things?
Yeah.
Okay. Just tell me and I'll switch over to the other side. In case of Mirage, you have the highway, you're driving over here, I'm sitting here, and instead of the rays going straight, they bend. Okay? And sometimes you basically creates a lens-like effect. And what you see in the picture is that you have the road that's going towards you, then you see the blue sky, right? That's reflected, and then you see the car that's coming on the other side. So you get this inversion. And that's very similar to this particular example, because the air near the road is very hot, and it's very luminous. Sorry?
Because of the Bragg scattering.
The Bragg scattering, yeah, there are other effects as well, of course. The total reflection and so on. Because again, change in refractive index of the air. Very minor change, but over kilometers. So anyway, the reason why I'm bringing this up is the way that's computed. Now you shoot a pilot star, and you want to figure out how the air is perturbing. How do they do that?
Ramesh,
Yes.
How are they going to image this pilot? So you say it's shooting laser, right?
Yes.
It should be reflected so that they could see it.
Now it ionizes the air,
Okay.
and you just see this bright spot at certain height.
And then they're compensating only for the atmospherical variation.
Exactly.
Because there are other deviations due to mass and everything.
And it's changing very rapidly. Every second, the air is changing. So even if you compensate for it once, that's not good enough because it's changing rapidly. Okay, so now you have the pilot star. How do you figure out how to deform those mirrors, right? They capture a light field. But this is not how they explain it. They explain it using the notion of Sharp-Hartman wavefront sensor. Okay, that's the terminology they use. And these are really expensive because they're very high quality. All they're doing is this wavefront is coming, and you have a lenslet array, very similar to the one we saw from Ted Edelson and Stanford. And the image that's formed here actually tells you how the light is bending. Okay? So let's go back to our picture here. We know that if you have a lens and the wavefront is traveling in parallel, where is the image formed for lens?
Focal.
At the focal length. Okay. Exactly at the focal length. If the wavefront shifts, where is the image formed? Slightly at a different location, right? So perpendicular and we shift. This is A, this is B. Image of A will be formed here, B will be formed here. Okay. So just again in wave optics, if the light is coming from here, the image will be formed here. The light is coming from here, the image will be formed here. The same thing. Now, what's happening over here is we don't have just one lens, but we have a set of lenses. have lens, 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 and so on. If we were looking at a very clear sky for the pilot star, the wavefronts will come parallel, and all the images will be formed exactly at the center. Okay. But imagine, because of perturbation, you have, I'll take a very simple example. You have something that's going straight and something that's tilted. Okay, very simple example. Now, what's going to happen is, for this guy, when it hits these lenses, it will again form the image at the same location. But for this particular one, which is tilted, the image will be formed somewhere else. Right? It will be formed slightly offset. So I can look up this image. Right? Originally the point was in the middle, and now after the aberration, the actual point will be shifted. So these two guys are fine, but these two guys, there is some shifting in the middle, and that tells you how the waves are bending. So you just feed this differential signal, you feed to the mirror, and the mirror will correct it. It's as simple as that. But this is also capturing the light field, because you can think of this as a propagation of rays. So in this case, the rays were traveling in straight line, parallel to the optical axis, and in this case, the rays were traveling not parallel to the optical axis. And so that's why when these guys hit here, they go slightly off, or when this guy goes, it goes straight. So the notion of light field is also very compatible with the notion of wavefronts. There are a few more details, but again, to keep it simple. It's also used in ophthalmology to look at any aberrations in the lens of the eye. Same exact idea. Okay, you have, let's see, you have the retina here. You're going to somehow send a beam and create a small spot. If everything is well, the light will go through it and it will create just a set of dots in the middle. If there is an aberration in the lens, this wavefront will bend and the points will not be at the center, but they will be offset. So in a single snapshot, I can tell you what the variation of the stream is. There's one critical element here though, that I'm not talking about, which is when you get this curve out, you don't really get the whole thickness or the depth of this curvature, but some piece of information is missing. What is that? What? The phase, or you get the phase, but you only get exactly. It's modulo 2 pi. It's modulo 2 pi. Okay, which means that if you, let's say, I put a piece of glass here, and the wavefront was delayed like that. Okay, and if I put, so let's say if the piece of glass slowed it down exactly by one wavelength. Okay. I can put the piece of glass with twice the thickness, and that will be delayed by 2 wavelengths. As far as the system is concerned, the phase delay is computed only by modulo 2 pi. So there's a phase wrapping that's going on. So if you have a shape like that, let's talk about it. So this picture here is actually showing that it's phase wrapped. So it may look like a lot of discontinuities, but basically you start from the edge and there's zero difference, and there's this curvature here is bent, and then it seems to be jumping from say here to here, but actually it's a continuous surface. It's just phase wrapped. And this concept is used in many other fields. If you're familiar with synthetic aperture radar or ranging, you get some values that are modulo of specific distance. So here we have, like the Fresnel lenses that you see on top of transparencies. If you have a lens like that, instead of creating a very thick lens, you can create a very thin lens, which basically chops this up. Okay. And you take this slope, put it here. You take this slope, put it here. You take that slope, put that here. The middle one is just piece of slab of glass, and so on. Okay. And this one, again, in simple cases, will behave identically. So, the flat magnifying glasses you can see, or the large Fresnel lens you put on top of the overhead transparency projector, they all work on this principle. The problem here is that at the edges, light cannot. So here there is a smooth surface. So even if it hits this is just conceptual boundaries. But if the ray intersects on this conceptual boundary, it doesn't really matter. It's still bend nicely. But here, if the ray hits one of the boundaries, it's going to scatter. It's not going to come out. So there are some issues there. But model those issues, this and this behaves the same. And here what we're doing is we're saying, I'm just going to chop this glass into multiple slabs, and I'm going to keep only the last slab. So I'm going to keep this one, and 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 then this one. So only the last slab is kept. And that converts a traditional lens into a Fresnel lens. And similar concept is also applicable for phase wrapping here. So then your doctor can see that in a perfect eye, all the points are in the center, but if there are any aberrations, the points will shift from the center, and all you have to do mathematically is these directions are giving you the gradient, 2D gradient, so you have to do a 2D integration to recover the surface. You have to solve the Poisson equation, and for those of you who are familiar on how to go from 2D gradients to 2D height fields, it's a straightforward process.
When they test your eye, which test is this? Is it the one where they scan a light on the back of your eye?
I don't have glasses, so and I don't have contacts. Anyone else?
Like light at different frequency,
Right.
different components are going to be delayed differently.
Exactly. Yeah, that's a very good point. That's a very good point. So, all these discussions we are having, we have on the board so far is for one specific wavelength. So let's say just a red color of light is going through this particular type of distortion. But if you have green light, blue light, or some other wavelength, then the distortions are a function of the refractiveness. The refractive index is a function of the wavelengths. So the distortions are also a function of the color. And so the aberration that you will see, or the focusing mechanism you will see, will be different at different wavelengths. And we will go into that a little bit later when we talk about color. So that was kind of a small detour of how waves and rays are connected, and how the concept of light field is used in many areas. Okay, so let's start having some fun with this sequence of images. Right? So we saw last time that you can see through occluders, and this is what you're going to do for your assignment. And think a little bit about how these different rays are allowing us to achieve these effects. Okay. Now, some of the slides will have some math and some geometry. So those of you who are interested, stay awake. Those of you who are not interested, you can ignore these slides. Don't go to sleep. But for those of you who really want to think about light fields, this is an extremely powerful concept. And when you visualize light field, people think about position and angle. Some people call it phase, space. In Fourier optics, it's space and spatial frequency. Some people call it spectrogram. And all it's saying is that, again, if you go back to the ray representation flatline, there's position and there's angle. So I can take this green ray and plot it in a position and angle space. Position is black and black. So there's x here and theta here. I'm going to take this green ray, find its x position, which is x1, and it's at a particular angle theta I, and I'm going to place that. There may be another ray that starts from the same point, but at a different angle. So the same position, but different angle. What about this one here? This one has different position, but same angle as the green ray. So x2 is a different position and an angle which is same as the red. Sorry, it's the same as the red ray. Okay. Is this diagram very clear? Because we'll keep coming back to this particular diagram. Okay. Now something we can start thinking about how light will propagate. And if you're doing the first assignment, the virtual optical bench, this is what you'll be doing. Okay. And once you see this couple of slides, it will be crystal clear how this is done. Now let's see this ray that's propagating from this plane to this plane. If it travels by a distance of z, I can write down the new coordinate as simply the original coordinate plus the angle times the distance. Typically, you would have a tan theta here, right? But in small angles, tan theta is theta, so we can just ignore that. And then the new x coordinate is just old x coordinate, angle times the distance. So how can you represent that over here? So if you look at the original points, okay, I'm going to take the green ray and change its x position, but its theta position is not changing because it's still going in the same direction. So its position is x1 prime, but the angle is still theta. Okay. So I will take this green guy and just shift it to the right to represent this particular one. So this one has shifted from here to here. And these other guys will shift as well. They all shift to the right if they're above this plane, and they'll shift to the left if they're below this plane. So you get a shear of the x theta representation. And this seems unnecessary. Why are we thinking about this dual space when we can just think about the primal space of the real world? But again, it becomes extremely easy to analyze it in this dual space of x theta. Is this clear?
I didn't get why the others were affected. If you were only moving the green ray, why did the others also affect?
So if I take now this particular ray, okay, think about what will x2 prime for that one will be. So we started with x2. Started with x2 and theta j. Okay, and now we want to find the new x2 prime. It's going to be x2 plus similar equation, z times theta j. Right. So it also has a similar shear. And depending on how far up you are here, the shear will be long. So this means that if the ray was actually parallel to the optical axis and perpendicular to this plane, x will not change and theta will not change. So if you are lucky enough to be on this equator here, on the optical axis, nothing will change for you. Same x and same theta. All right. So let's do a couple of quick exercises to make sure we are all on this. If there is a point and a light source, and here is an example where the light field is very simple. Right? I have a bulb or a LED, better, and it's emitting light in all directions. How can I represent that in the x theta space? So there's a particular x. I'm going to put it somewhere here, and it's going to span all the thetas.
Vertical line.
Right? So it will be a vertical line. Very good. Now, if I let it propagate, or let's say I have a new light field here, where the light is very, very far away, and all the rays are coming at 10-degree angles with respect to the optical axis. What will we see? A horizontal line, because we are spanning all the x coordinate, but only the theta of 10 degrees. And that's what we get. Right. So two very simple examples. Point that's very close, vertical line. Point that's very far away, think about a star, horizontal line. Okay. Just by using these two, we'll be able to build a lot of machinery to understand how we can create some really amazing effects for using light fields.